Today we try to find a way to assess the primality of an integer, that is to determine whether an integer is a prime number. Now, first of all, when we say an integer is either prime or not, this involves a Boolean logic in which we only have two possibilities, which are generally denoted true and false. So following this logic, for the first 7 integers greater than 1, we should have 2 that goes with true because 2 is prime, 3 that goes with true as it's prime 2, 4 with false, it isn't prime, 5 true, 6 false, 7 true, 8 false. This duality between true and false reminds us of the binary system of numeration, which comprises only 0 and 1. And since it's easier to do mathematics with numerical values than qualitative ones, that's what we are going to continue with. And in that vein, true will correspond to 1 and false to 0. Therefore here, for 2, we'll have 1, for 3, 1, 4, 0, and so on. Therefore, we have a correspondence between integers greater than 1 and either 0 and 1. And in mathematics, when we talk about correspondence, we talk about function. Therefore, determining whether an integer is a prime number comes back to determining whether it corresponds to 1 and 0. And that correspondence, which is a mathematical function, is what we aim to discover here. Let's call that function k. Right? Now, k is defined from the set of integers greater than 1 to the set 0, 1. And for each input, it produces 1 if the input is prime and 0 if the input is not prime or composed. Now, to determine an expression for k, right, we will consider the two cases separately, and we start with the case of prime numbers. Case of prime numbers. Now, consider a prime number p. Since p is prime, it means that p has only two divisors, one in itself. Therefore, for any integers less than p, the greatest common divisor between them is 1. That is, if you have a certain I, right, an integer I, which is between 1 and p, then a GCD of I p is equal to 1 because p is prime. Therefore, GCD of 1p equal to 1, GCD of 2p equal to 1, until GCD of p minus 1p equal to 1. And when we sum all these values, we have sum of I going from 1 to p minus 1, or GCD of ip equal to p minus 1. Now here, our sum goes up to p minus 1, and we want to close it to p, so I will add the GCD of p and itself here. So the GCD from 1 to p will be equal to the GCD from 1 to p minus 1 plus the GCD of Pn itself, which is equal to p minus 1 plus p, which is equal to 2p minus 1. Now, we have got an equality here, and we are looking for an expression that gives 1 when n is prime. Since there's an equality and both sides of the equality are different from 0, it seems pretty intuitive to make a division here, and that's what we are going to do. We divide the equality by this side, which yields 2p minus 1 divided by the sum of the GCD 2p, which gives 1. So finally we find an expression that gives 1 when the input is prime. This gives us the first hint of what k might look like, but we can't make any conclusions yet without looking at the case of composed numbers. Here, consider a composed number c. Since c is not prime, it means that there exists at least one divisor of c that's different from 1 and c itself. And for that divisor that we will call d, well, the greatest common divisor of c and d is equal to d. It is certainly greater than 1, since d is strictly between 1 and c. Now, since we have at least one divisor for which the greatest common divisor is greater than 1, well, when you look back at this sum here and you want to do the same thing for c, then it is certain that the sum of the GCD of I and C, where I goes from 1 to C, is greater than 2C minus 1, because we had an equality in the prime case, and in the prime case everything was equal to 1. Here we have at least one case that is greater than 1. Therefore, the sum must be greater than 2C minus 1. And so, by operating the same division as last time, we get 2c minus 1 over the sum of I going from 1 to c of GCD IC being less than 1. Well, this isn't quite what we are looking for, since we want an expression that gives 0 when n is not prime. But we can observe that both parts of the quotient are positive. 2c minus 1 is greater than 0, and the sum here is greater than 0. Therefore, the quotient as a whole is also greater than 0. And now, since this quotient is a number strictly between 0 and 1, then it is certain that it rounds down to 1. Wow, now, when I say round down here, I'm talking about the rounding down function, which is expressed this way with these symbols here. To give you an example, if I have 2.7, right, the rounding down function gives 2 with 2.7. Similarly, 3.1 rounds down to 3, and let's say 53.7 rounds down to 53. So if I have a number x, and x is between 0 and 1, then x necessarily rounds down to 0, and hence this expression here rounds down to 0. Yes. And now we have an expression that produces 0 when the input is composed and 1 when the input is prime. But they are quite different. However, it's not a problem because since this quotient here gives a whole number, and that whole number always round down to themselves. So 1 rounds down to 1. Therefore, this quotient here, 2p minus 1 over the whole sum, rounds down to 1. Hence, we finally have an expression that produces 1 when the input is prime and 0 when the input is composed. And this gives us an expression for our function k. K is a function defined from the set of integers greater than 1 to the set 0, 1, which converts each n into 2n minus 1 over the sum of the GCD of in, where I goes from 1 to n, all rounded down. This function gives, in a single expression, the primality of the function k. So for example, k of 2 gives 1 because 2 is prime, k of 6, 0 because 6 is not prime, k of 1 is, well, undefined because it's only for integers greater than 1, k of 23 give 1, and so on. This is a very interesting function. I appreciate the fact that it gives the primality in just a single expression, and you just plug in the value, and from the result you can know directly whether the number is prime or not.